All right, in this video, I'm going to provide the calculus-based derivation for the work energy theorem in one dimension. To really get into 3D derivation, you really need to know calculus 3 stuff, vector calculus. And in this class, I'm basically just going to give you the formula for 3D. You won't really need the technical stuff, but I want to present the real deal as well. Okay, so the one-dimensional derivation of the work energy theorem isn't too bad. It proceeds very similarly to what we did for impulse and momentum. So if you remember, with the impulse and momentum theorem, we started with Newton's laws, and then we performed an integral of motion. We integrated, in that case, we integrated Newton's laws over time to calculate, or to find the work, or sorry, the impulse momentum theorem. We're going to do something kind of similar, only we're not going to integrate over time. We're going to eventually integrate over position, but it's going to be a little bit more complicated than that. There's a sort of a trick. It's one of these tricks that I saw as a student, and I thought, man, I wouldn't have thought of that, but after you see it once, it's like, oh, I never forget it either. And you'll see it in dynamics, and you'll see it in other classes. It comes up a lot, just in various derivations. So here we go. The starting point, well, let's define our system first. So let's imagine that we have a cart, an object, and it's moving in one dimension, and there can be forces acting on it. You know, you got a string pulling on it, whatever. But we only focus on the horizontal motion of things. And these forces don't have to be constant. They can be arbitrary. Okay, they can be anything you want. So we start at a place where we are solid. We start in a position of strength. We start with Newton's second law. So we say F net equals the mass times the acceleration. And we're going to rewrite acceleration. We're going to rewrite this as F net equals mass times the derivative of velocity with respect to time. And we don't have to worry about vector stuff too much because really these are in one dimension. The vector part's just a minus sign, so that's okay. These things can be positive or negative. All right. Now, here's the trick that I wouldn't have thought of when I was a student, I don't think. And but after you see it once, hopefully you can remember it. Multiply both sides by velocity. Okay, that's fine. And then notice something. Maybe I should do that over here. The derivative with respect to time of velocity squared equals twice the velocity times the derivative of velocity with respect to time, using the product rule. And that's always the case. So for any function, the derivative of the function squared is twice the function times its derivative. What that means is that if you have a time derivative, you can multiply by the thing which is being differentiated and then rewrite that as the velocity times the net force equals the mass times the derivative acting on the velocity squared. Oh, I'm not there yet. I have to divide by 2. Okay, so if I want to have velocity times the derivative of velocity, I have to divide the 2 over to the other side. So what we've done is we've taken something and we are performing, we've got it into something that we can integrate and recognize this as a total derivative of something else. So all that remains here is I'm going to move the constants inside the formula, and I'm going to write the velocity times the net force, which could be variable, it doesn't have to be a constant, equals the time derivative acting on m over 2 times the velocity squared. All right, now let's integrate both sides with respect to time. So on the left-hand side, I'm going to have integrate with respect to time. So I'm going to write that as F net, say from time 0 to some other time t, times the velocity times dt, equals the integral of this total derivative. But that's nothing other than, when you integrate total derivatives, that just gives you the change in m over 2 v squared. This is what we call kinetic energy. All right. So kinetic energy pops out much as it did before. This other thing is what we are going to call work. You might be saying to yourself, wait a minute, you said I'm going to have an integral over position, over space, or distance. That looks like an integral over time. And to do that, we have to be very careful. And we check. I'm in the math room where the mathematicians teach. So I have to make sure that none of them are lurking. But given that it's about 10 o'clock at night, I think I'm safe. And what we do is we rewrite this velocity as dx dt. And that allows me to pretend the differentials are fractions and they can cancel them out. And I end up with the following result. I end up with the statement that the integral of the net force dx from the x initial to x final equals the change in kinetic energy. Apologize. Okay. This is the real definition of work in one dimension. Right? So, if you're walking in the positive direction, then you're increasing x. So it's kind of like you're integrating in the correct way. If you walk in the negative x direction, then if you're walking backwards along the real line, then your lower limit is bigger than your upper limit, and you're going to get a kind of integrating backwards. On the other hand, if you integrate backwards, but you have a negative force, you get a double minus sign, and this integral would be positive. So what I'm saying is, if you're walking forward and the force is forward, double positive, it's all positive, positive work. If you're walking backwards and the force is backwards, double positive, you get a positive work. You're going to speed up by going in the backwards direction. If the force is negative and the displacement is positive, you're integrating forward, you get a minus work. And if the force is negative, if the force is positive, but you're walking backwards, you get a negative work. Let's do that in pictures. We learned that work is nothing other than the area under the force versus position graph. So if I have some force, the area under this gives me work. So if you have a positive displacement, that means that means you integrate from small x to positive x. So positive displacement, positive delta x, would correspond with moving to the right. So you're doing the integral in the right way, the way you learn in Calculus 1 most of the time. On the other hand, if you walk backwards, it's like doing your integral from large to small, and you know that gives you a minus sign when you perform the integral. You get a negative area. So if you think about all the ways you can have pluses and minuses, you can get a minus sign coming from having a positive force or a negative force. You can get a minus sign coming from walking to the right or walking back to the left. And double positive and double negative give positive area, and negative positive or positive negative give negative area. And that determines whether the work will be positive or negative. Okay, this is the actual version of work, the real version of work. Let me do a simple example then, and we'll stop this video. Well, you can do anything, really. Given this, anything that you can integrate, you can do it. So, for example, I don't know. Let's say we have some crazy function, like the force acting on the cart. Let's say it starts out at 0 and finishes as a constant. So let's say it's like 1 minus e to the minus 2x, and so if you plug in x equals 0, you get 0. If you plug in x equals infinity, it goes off to, well, this will go to 0, it goes to 1. Okay, so this would be a function, if I was to graph it, this would look like start at 0, finish at 1, and asymptote. So it'd be something like that. Okay? And we'll just say that it's measured in newtons, like that. Strictly speaking, because exponentials are transcendental functions, they should be dimensionless. So I want to do 2 times position over a meter, just so that the units come out right. You have to be a little careful with the units here. All right, let's evaluate the work in traveling from x equals 1 to x equals 5. So let's evaluate the work, which would be nothing other than the area under this curve, and that would give us the change in kinetic energy of some problem. So the work associated with this force and moving from x equals 1 to x equals 5 would equal the integral from 1 to 5 of f dx. That's nothing other than the integral from 1 to 5 of 1 minus e to the minus 2x. I'll worry about units. Well, all right, let me be careful. M dx. All right. This is an integral of a sum, but integrals are linear, so the integral of a sum is the sum of the integrals. So I can integrate 1 from 0 to 5. That just gives me 5. So that gives me, let's just be careful. That's x, because I integrate 1, that's x to the 0, add 1, divide by 1, gives me x. With the power rule, minus, well, let's think about that. The integral of an exponential is another exponential, but it's an exponential with a coefficient. So you have to use you could say u substitution, or you do the opposite thing you would for derivatives. So if I took a derivative of this, I would get minus 2 over m. So I'm going to integrate this, I'm going to get minus m over 2. And then I have a minus sign out front. So that becomes plus meters over 2 times the exponential, e to the minus 2x over m. And I have to evaluate that between 1 and 5 meters. Trying to be careful with all the units here. It works out. If you're on top of the units, you don't have to put them in. You just know what it should be, and it'll be okay. But on the other hand, it's good practice to do it, and it helps us sort out any mistakes we might make. Okay, so this is just some crazy example, and no surprise, we get some crazy formula. So I evaluate this at the upper limit minus what I get at the lower limit, and that's going to give me 4 meters plus e, wow, so I'm going to get a meter over 2 times e to the minus 10 minus e to the minus 2. I'll let you go. You guys can type that in. So if you want to regroup it, you can just say that there's an overall factor of meters there. So it's 4 plus a half times that stuff in parentheses. And then to get the units right, you should multiply by meters, and it comes out the way it should. Okay? So any function that you integrate, that could be a possible force. That's how you would handle it.